Good morning, everyone. This is the first segment of section 3.2. 3.2 is actually a pretty short section in the text, but I think we'll try to take this one a little bit slow because it involves some concepts of rotations and circles. And for whatever reason, it's been my experience that when we get to this arena, students often have a little bit of difficulty trying to put that all together. But realistically, section 3.2 is all about one formula, and that formula is embedded in the definition of a radian measure of an angle. So hopefully I can kind of make this pretty simple, and then maybe use a couple of examples to try to illustrate the point. So let me get over here to my document camera, and I will introduce some ideas. There's some pretty standard symbols that are used in rotational mechanics, and the textbook advocates for one particular kind of that. So let's see, we're in section 3.2, page number 1. Okay, so recall that when we defined the angle in radians, so an angle in radians, and I'll just name that angle theta, is defined as the ratio of the arc, the length of a circular arc between the initial ray and terminal ray divided by the radius of said circle. Now, in order for this to work, and this isn't a formal definition really, I'm just trying to pick out some details here, because you also need the circle to be centered at the vertex of the angle as well, which I mean, I guess I could add that, and this really sounds like something very formal. So provided the center of the circle is coincident with the vertex of the angle. Now, this allows us, I suppose, in some sense, to create negative angles. This isn't something I'm going to really go into too much, but we sort of impose the SIGN of the measure of an angle is dependent on the direction of rotation. So the counterclockwise rotation arc lengths are said to be positive, and clockwise rotations would be negative. I mean, it kind of is, we're getting into the weeds there a little bit, because the big takeaway here is that this definition of angle leads immediately to an equation. So let's say, let s, lowercase s, be the arc length, and r be the radius. And I'm talking about these terms that are defined up here in this sort of pseudo definition. So from this we get an equation that tells us what the radian measure of an angle is. now that all the symbols are defined. So theta, by definition, is the arc length divided by the radius. And I will say theta in radians. Now this shouldn't seem like some sort of hieroglyphics or anything that's incredibly extraordinary. What we've simply done is we took this idea, which we described last time, and we've written it into an equation. And it turns out that this equation is pretty useful, but I'm going to use it in a different format where we have S equal to R times theta, where again, theta in radians. Okay, so a bunch of preamble just to start talking about gears and pulleys and different kinds of things like that. So consider for a second, let me get this sort of started here. So let's use this for something. So normally what we're talking about is not really trying to measure angles, but we're measuring parts of circles in different ways. And maybe we want to know the arc length associated with an angle, or maybe we want you know, a number of revolutions or something along those lines. One of the things that you're going to find in this chapter is there's a lot of unit conversion going on. So we're much like what we did in previous chapters where we converted from degrees, minutes, seconds to decimal degrees or vice versa. That's pretty trivial. But when we start talking about converting between radians and degrees and revolutions and different things like that, it is a little bit more challenging, and the book does it to you on almost every problem. So you very rarely are given the angle in radians, and yet the formula that we have that relates arc length to radius is in radians. So we need to develop some skill at conversions and then what we might use them for. So let me give you an example. So suppose we have a circular wheel doesn't really matter if it's open or closed, but whose radius is 25.60 centimeters. I notice that has 4 significant digits. So the question is, what arc length corresponds to an angle of, and I'll have a couple different examples here. How about the easy one, which is 7 pi over 8 radians, and let's say 54 degrees. And let's throw another one in there. How about 2.3 revolutions? Okay, so first off, recognize that almost every problem that comes out of this section involves that equation that we had, S equal R theta. So it's about identifying what variables you have that are stated in the problem. I mean, there's really only 3, so you have to have 2 in order to be able to find the third one. It's pretty elementary algebra at that point, but you have to be careful about making sure that everything's in the right units. So the first one is relatively simple. Now, when you see an angle measured this way, okay, I'm just going to bring up this idea just briefly, but I want you to think about significant digits because they're kind of important here. How many significant digits does this thing have? Well, when it's written this way, this is an exact angle, which is kind of something we haven't seen too often, where it's just like it's exactly some number. So this has an infinite number of significant digits. So we're going to end up multiplying. And when we multiply something that has an infinite number of significant digits times something that has 4, well, we're going to end up with something that has 4 significant digits. This one, this 54, it does not have 4 significant digits. It only has 2. So when we multiply these two together, we'll end up with something with only 2 significant digits. And similarly with this revolutions business, this is a measurement of some kind and only has 2 significant digits. So when we end up doing the multiplication, we have to do some conversions on both of these. But when we do those multiplications, we'll end up with something that only has 2 significant digits. So just bearing that in mind. So for the first one, notice every one of these problems is solved by S equal R theta, where theta is in radians. That's kind of, I mean, that's not part of the equation. That's just something I write down every time just to remind myself. Everything in this, we'll look at a couple different formulas in this chapter, and they all sort of require that you put theta into radians at the very first. So for this part A, S is equal to the radius, which is 25.60 centimeters, times the angle in radians, which is 7 pi over 8. And when you work out that multiplication, I'll just do it right here where you can see that. Light's a little funny, but we have 7 times pi divided by 8. So this is the sort of numerical value for the number of radians, 2.75 more or less. And then we're going to multiply that by 25.60, and we end up with 70.37, blah, 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 blah. Now, I'll go ahead and write down a few of those. 1675, and just call it good. This is in centimeters. And now we apply the rules for significant digits, which is to count up the number of digits of the two products. Remember, this is infinite, this is 4, so we need to truncate this down to 4 significant digits. So our answer is 70.37 centimeters. Okay, let's try the second one. So B, we have S equal to R theta, and I'm not going to write it here, but it is in radians. So the equation is, again, it's the same radius, so 25.60 centimeters. And here we'll need to do kind of, maybe if I kind of, I mean, I wouldn't normally do this, but let me sort of bracket this off and say, this is what I'm doing. I'm multiplying 54 degrees times my conversion factor from degrees to radians. Okay, this is the conversion taking place. And so when I do all that manipulation, so I've got, start with, I usually like to start over here with the conversion, because then I kind of hopefully can catch many mistakes, because I know sort of offhand that a 1 radian is 57-ish degrees. So if this number doesn't come out to just a little bit below 1, then I know I've made a mistake. So 54 times pi divided by 180 degrees. Notice that's 0.94, blah, 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 as expected. And then I'm going to multiply the whole result by 25.60 centimeters. So there's my sort of raw number, which is 24.1274, whatever. And to truncate it properly, because we only have 2 significant digits in the measured quantity, 4 here, it's a product. Notice this one has an infinite number. Again, that's a conversion, and so there's an exact relationship between these, which means there is an infinite number of significant digits. So the only one that's the limiting factor is this 54 degrees. So the answer to this problem is 24 centimeters. Okay, so let's move on to the third example here, or the third problem, which recall was to do it for 2.3 revolutions. So part C, same thing as before, S equal R theta. But again, theta has to be in radians. The measure of the angle that we have is not in radians, it's in revolutions. So what's the conversion between a revolution and a radian? Well, one revolution is one lap around the circle, which we know is equal to 2 pi radians. So the conversion is 2 pi radians equals 1 revolution. And so as I'll kind of force feed it here a second. So S will be equal to 25.60 centimeters. And again, I'm going to use some extra parentheses because what I'm converting is 2.3 revolutions. And I'm going to multiply that by, remember, I want the sort of unit I'm aiming for, divided by the unit I'm starting with. And notice, anytime you have one of these conversions, you should be able to say numerator equal to the denominator, and that should be a true statement, right? So 2 pi radians is 1 revolution. So when I multiply this business out again, I'm going to expect to get, well, I mean, I'm dividing by 1. So it's 2.3 times 6, should get about 12, 13, somewhere in that neighborhood. So 2.3 times 2 times pi, 14.45, whatever, that's sort of my raw number. And then I'm going to multiply that by 25.60, okay, which comes out as, I don't know if you can quite see where the decimal place is, but it's right between these two nines. So it's 369.9539 something centimeters. Okay, and so again, applying the significant digits rule, I've got something with 4 digits times 2 digits times an infinite number of digits. The smallest number is 2, so this can only have 2 significant digits. So this becomes 370 centimeters. Okay, so that's a pretty simple example involving a wheel of a known radius and a certain distance. Now, if we had looked at a problem maybe where we take the arc length and a certain number of revolutions or something like that, and find the radius, I will probably do that in the next segment. I think this one's probably getting a little long, but I will probably just start on the same piece of paper and keep going with page 3. So I'll see you back here in just a second.